Good afternoon. This is a tutorial video on certain fundamental chapters of heat transfer. We'll be dealing basically with two chapters. The first one is an introduction to heat transfer, wherein we understand what is the difference between heat transfer and thermodynamics, what are the different modes under which heat transfer occurs, what are the different laws that govern heat transfer. And the second chapter is considering the conduction process in specific for heat transfer. Before we get on to the tutorial, I would like to introduce myself. My name is Nachiket. I have done my graduation from Shastra University in the field of mechatronics. I passed out from there in the year 2012, and in 2012 I cleared my GATE Mechanical Engineering with an All India rank of 83 and got admission into IIT Bombay for Industrial Engineering and Operations Research. That's about it for myself, and let's get started. So what exactly is heat transfer? Now we know that heat is a form of energy. Now whenever the word energy comes into mind, there's this fundamental law that the entire energy in the universe is constant. You can change it into one form to the other, but the energy as such remains fixed. So heat energy is flows from one body to another only when there is a difference in temperature between both the bodies. Else the process does not happen. For example, when we look at the wind blowing, the wind blows from one direction to the other because there is a difference in pressures in both the sides. So here the pressure plays a role when the wind is blowing. Similarly, the temperature plays a role when the heat transfer is actually occurring. Now, why do we have to study heat transfer separately and thermodynamics separately? That's because thermodynamics tells us about processes which are in equilibrium. It tells us in equilibrium what are the temperatures of the body. In equilibrium, what is the total amount of energy that is transferred from one body to another for after it reaches equilibrium. But in heat transfer, we understand the time taken for the transfer of heat from a hotter body to a colder body. It makes us understand what is the different temperatures through which the body passes through. An example of this would be taking a heated rod and placing inside water. Now thermodynamics will only tell you that after the entire process is done, in equilibrium, what is the temperature that is achieved by both the water as well as the heated rod. But heat transfer will tell you how much time it's going to take. It is going to tell you what are the different temperatures on the surface of the rod as well as inside of it. Now that is the difference between heat transfer and thermodynamics. Now let's understand what are the different modes of heat transfer. There are basically three modes of heat transfer. The first one is called conduction, second is convection, third is radiation. The conduction mode of heat transfer can only happen when there is a direct physical contact between the bodies that are concerned. For example, body A, body B, which are at two different temperatures, that is when alone the heat transfer actually occurs, are in direct physical contact. Through the contact, the heat passes through from the body at a higher temperature to a body at a lower temperature. Now let's take convection for example. The convection process of heat transfer will only occur when there is a fluid involved in the entire process. The fluid could be in a gaseous state or in a liquid state. Now an example for this would be taking an immersion rod, a daily example, and trying to heat water. Now essentially what is happening is water, when it gets heated up, it expands, and given that the mass of the water is constant, we find that the density varies. Now as the volume is expanding, the water becomes lighter, so it raises up because there is a difference in density, so there is a buoyancy effect that is occurring within the layers of the water. So the cold water is heavier than the hot water, so it settles down, and when that gets heated up, it raises up again. So this entire process involves a circulation of the molecules of water themselves, and that is how heat transfer is occurring. Now this very example was an example of a natural convection, wherein we are not applying any pump or blower to force the air or the water to go to the heated medium. But there is another way that the convection can be done, which is by using pump or a blower. That is wherein you use an external source to force the fluid to go towards a heated object and then get heated up or cool the other object. That is convection. Now coming to radiation. Now radiation, in this process, we do not need a medium for transferring. There is no requirement of a medium for transferring of heat. A best example for this would be the sun and the earth. Now the space is absolutely empty, it's a vacuum, there are no air molecules there, yet we are able to receive the heat from the sun on the Earth's surface, and that is happening through radiation. Now that we have seen three different modes of heat transfer, there are different laws that govern these different modes. Now we do understand that as there are laws that govern motion, there are laws that govern heat transfer. Now let's see what are those laws. Coming to the first law, which is the Fourier law. Now the Fourier's law basically tells that your heat Q is proportional to the area which is normal to the surface where heat is getting transferred. So if this is your surface and the Q is transferring in this direction, so this area is considered. So Q is proportional to A. It is also proportional to the change in temperature in the direction which we are considering. So for example, if this is my x direction in which I am trying to observe, and this is the temperature profile, that is at one end of the surface it is T1 and the other end it is T2, then my heat transfer is depending on the gradient meaning slope. So it depends on the slope of how my temperature is changing in the direction of x. So we can write this as Q is proportional to A multiplied by dt by dx. Now to get rid of this proportionality constant, we have Q equal to minus K A into dt by dx. Understand that we have taken this minus sign into consideration because there is a decrease in temperature profile. Here T1 is higher than T2, so we find that the slope is actually negative here, and so this negative sign is put here in order to make Q positive. So this is essentially Fourier's law of heat transfer. This is usually used for conduction processes. Right. Now we come to the convective law. The convective law, or also known as the Newton's law, says that if you have a surface S here and there is a fluid which has a temperature, let us say T infinity, and this has temperature Ts, so then my transfer of heat from the fluid to the surface, which is Q, is proportional to the area of contact between the fluid and the surface. It is also proportional to the difference in temperature between the fluid and the surface. So we can write Q is proportional to A multiplied by T infinity minus Ts. Now to get rid of this proportionality constant, we have Q equal to H into A into T infinity minus Ts. Now describing what does this K and what does this H actually represent. This K is a physical property. It's basically telling you how the heat gets transferred through the body, how easily it can get transferred through the body, more specifically. So if your K is high, which means that object can transfer heat easily. Now such objects that we observe in our daily life are metals. That is how, that's the reason why I use metals for cooking food, because it allows easily the heat to pass through. We find that this K as a property behaves differently for solids, liquids and gases. We find that K actually decreases with increase in temperature for solids as well as for liquids, though there are exceptions in both the cases, like aluminium and uranium in case of solid and water in case of liquids. But in the case of gases, we find that it increases with the increase in temperature. Now the question is, why does this happen? Why is it that for a gas, the K value actually increases with increasing temperature? And this is because as you keep heating a gas, though they are very far apart, as you keep increasing the temperature, the number of collisions between the gas molecules keep increasing, and it increases quite quickly. And it is through these collisions that the transfer of heat occurs much faster. So that's why you find that by increasing K, the gases actually transfer heat more quickly. Now, this was the role of K. Now, for H, we find that it is basically used in case of a fluid medium that is taken whenever a convective heat transfer is taken into account. Now coming to radiation, in radiation we find Stephen-Boltzmann's law, which is being used, wherein it says that it considers a black body, wherein it says the heat transferred, the rate of heat transferred by a black body is proportional to the fourth power of the temperature and is also proportional to its area. So we find that this Q is proportional to A into T power 4. So again, to get rid of this proportionality constant, we have Q equal to sigma, which is the Stephen-Boltzmann's constant, A into T power 4. Now in order to, it is very essential for us to know these units, their values, and specifically, more importantly, their units, which can be easily found out by just rearranging the equation. Let's say, for example, if we are taking Q equal to K into A into dt by dx, so we want to know what exactly K is. So we say K equal to Q divided by A into dt by dx. We say that Q, which is energy, is in terms of watts, because we are talking about rate of energy transfer, so it is in watts, and area, which is meter square, and let us say temperature is in Kelvin per meter, so we cancel this off, so we have watts meter Kelvin. So this is how you can get to know what these proportionality constants are. So in the first chapter we have basically seen what are the different modes of heat transfer, what is the Fourier's law, we have seen what is convective law or the Newton's law, as well as we have seen the radiation law. Now that we have come up with these equations, in the second chapter we would understand that how Fourier's law will be used to define how the conduction heat transfer process would occur. We would understand it much better by using Fourier's law, and that will be in a separate video. Thank you.